S0 is set to what? -5 is also the value in decimal base of this signed binary number. Okay. So this simple example illustrates how to implement SDT in practice. Okay. Of course, it's just very simple example. Now, we also need to handle another issue. How can we perform semantic action at other points in the parsing process? Okay. Once again, I want to remind you that for technical reasons, we always insert semantic action to the right hand of production part, body part, okay? But in design, in many cases, we need to insert semantic action to somewhere inside the body part. Sometimes we need to perform semantic action on a shift action, not on a reduced action. Okay? This is our solution. In this case, we have to transform our framework to satisfy the basic principle. Okay? Now, look at the first issue: how to perform a semantic action inside the body part. The solution is simple. This is the original version. Okay, we propose a new non-terminal symbol, and that symbol will be inserted into the part where the semantic action should execute, right here. And this is the new version of this production. Okay, and in the next step, we add a new production in which the semantic action is in the right hand of the new production. Okay, obviously, using this trick, we can always move what? Semantic actions to the end of a production. So this problem was solved completely using this trick. Okay, I say again. For each semantic action, we create a new non-terminal symbol. Okay, and that semantic action will be replaced by the corresponding, the created non-terminal symbol. And then we add new production in which the semantic action is in the right hand of the new production. Okay. What about the second problem? We need to perform semantic action on a shift action. Okay. Once again, we have to rewrite our framework. And I think this solution is best described through an example. So this is paragraph. Suppose that we need to perform a semantic action Whenever the parser shifts the terminal symbol bit, suppose that. Okay? So the solution in this case is what? First, we add this production to our grammar. Okay? And then we replace every occurrence of this terminal symbol with this non-terminal symbol. Of course, this is the new non-terminal symbol. Okay? Now, can you see? Obviously, in this case, we need to perform semantic action on a shift action. Okay? Right after this shift action, we need to perform this one. And the solution is what? First of all, we create the new production. We replace the occurrence of what? Of bit by this new non-terminal symbol. And then we move the semantic action to the right hand of the new production. Then, once again, using this trick, we can always move semantic action to the right hand of production. Okay? And remember that it's essential that these two versions generate the same language. Okay? Now, another role of semantic analysis is to perform time checking. Do you remember? Time checking. And now we consider a more complex, more complicated example. In this example, we design an SDT to perform time checking. Okay? Now, this is very simple grammar. So, tell me something about a program written in language generated by this grammar. Some characteristics of a program written in the language generated by this grammar. Defined by this grammar.
Ambiguous.
Ambiguous? Yes. That's right. It's ambiguous. But you know, we do not focus on the correctness of grammatical rule in this lecture for simplicity, for clarity of vision. Okay? Right now, we concentrate only on what? On the design of SDT for implementing time checking. Do you agree with me? That's right. This grammar is ambiguous. Okay? But we do not pay attention to such a thing right now. For simplicity, for clarity of vision. Okay? So let's assume that it's not ambiguous. Tell me something about program written in this language. Close your laptop. Now, stand up. Tell me something. A program in this case contains at least one declaration statement. Okay, and the declaration is followed by only one expression, and this is the form of an expression. Okay, what else? Each declaration statement must be ended with semicolon. Okay, someone says semicolon, someone says semicolon. What else? What is the form of a declaration statement? To the left of column is an identifier. To the right of column is a type. Okay, and this is the list of types in this language. For simplicity, let's assume that the lower bound of the range of the index is 0. Similar to C programming language. Do you understand? Now, tell me, can we declare or use a multi-dimensional array variable in this program, in this language? Yes or no? Yes, we can. Because T, once again, can be described by this one. Okay? So, in this case, we may declare or use a multi-dimensional array variable. Okay? Now, take your time to verify this stupid program. Are there any type errors in this program? Syntax error, excuse me, syntax error. Let's assume that it is not ambiguous grammar. It is bug free. Okay. Now, this is our SDT. We use this SDT to perform type checking, and it's very simple SDT. I do not show the first two productions, okay, because they have no semantic actions. Read this slide carefully. Do you remember pointer or array? These two terms. They are what? Type, constructor, operator. Do you remember? Type, constructor, operators. Do you remember the meaning of this seller function? Yes. is used to gather information in the corresponding entry in simple terms. Okay. Now, let's see, for example, this semantic action. This reference is legal if the type of index is right or subscript is integer, and the type of what can I say in this case, the type of type, E1 type must be described by this type expression. Okay, it must be a right type, and then the type of this reference is T. Okay, otherwise our compiler delivers a type error. Okay. Now, this is another program written in our simple programming language. Okay. The first line indicates a declaration, and the second line is an expression. And of course, it's bug-free. Okay. It contains no syntax error, and this is our parse tree. You know, you all know this. Semantic action will be illustrated in parse tree as a special node. The node that has no child node. Okay, so in other words, we say each semantic action is a node in parse tree. Okay, once again, we use the post-order trapezoid of the parse tree to simulate the running process. Running process in this case is to perform type checking. Okay. And what is the first semantic action? The semantic action which is activated first is this one. Okay, using post-order trapezoid of the parse tree, we can say this is the first semantic action, which is count. Okay. Now, T derived character. The semantic action tells us that T dot type is set to character. Exactly. What is the next semantic action to be executed? This one. Okay. T derives circumflex T. Look at this. Then T dot type is set to this value, this type expression. Exactly. And it is the next semantic action. Explain by yourself the result of this action. Look at this one. Okay. Obviously, in this case, T dot type is set to this value. You repeat using this semantic action. And you know, this information will be sent into the symbol table using this pseudo function at type. Okay. In other words, after compiling declaration, our compiler knows the type of variable A. Okay. And information about the type of variable A is stored in the corresponding entry in the symbol tables. And now let's consider the statement. In this case is just an expression. You see, the next semantic action to be executed is this one. Okay? And derived ID. Derived ID. Lookup function returns what? Returns the type of this identifier. In other words, the type of this identifier is what? The type is described by this type expression. Okay? Each time our compiler use the information collected in previous stage. Look at this. And this is the next semantic action. And number 5 means the type is integer. Okay? And what else? What else is meant by yourself? A file circumflex. Okay. In this step, we focus only on this part of our expression. So our compiler determines that the type of this part is what? Pointer to character. Okay. And finally, look at this action. It knows that the type of this entire expression is what? Character. Okay. So this is the way we teach our compiler to perform type checking. Okay. Now, in this example, I expanded the previous grammar to get more complex contextual grammar. Okay, and once again, can you see? This is the ambiguous grammar. Why? Get this. If A is not equal to B, then A is set to B. B is set to A. Yeah. Obviously, using this grammar for this input, we can build two different pass trees. You agree with me? In one pass tree, we say this statement belongs to each sector. In another pass tree, we say these are two separate statement. Okay, but once again, for clarity of vision or simplicity, we ignore such a thing. Okay, and let's assume that in this grammar, if statement, while statement contains only one statement, Okay, this is our assumption to eliminate the ambiguity in this case. It means that based on our assumption, we say these are two separate statements. Do you agree with me? I say again, we do not pay attention to what? To the correctness of grammar, syntax grammar. Okay? Right now we focus on how to design an SDT. Okay? How to perform semantic analysis. And this is the new part of our SDT. I cannot show the entire SDT in this case because we have not enough space. Okay? I just give the new part of the SDT. Can you tell me something about what it's just a special type defined by compiler writers, defined by programming language designers. Okay? What is the role of special type in this case? This type. In this case, programming language designer says that a statement is legal if and only if its type is this what. Okay. Now, first of all, this statement represent the list of statements. Okay, and of course, the type of the list of statements is what if the type of this statement is this one. Okay. What else? Look at this. Subject action. We say this expression is legal if and only used for operations on integers and floats. Okay, these are two reasons why our compiler needs to transform the type of operands. Okay, and in this example, we focus only on addition operator. Okay, and the transformation in this case is called implicit type conversion. Do you remember this one? Okay. Now, for simplicity, let's assume that the type of operand is either integer or float only. Okay. Now, how can we perform time checking for expressions with operator addition? This is our SDT. Remember that for simplicity, we say the type of operand is either integer or float only. Okay? It's easy to understand, is that right? If the type of operand is integer, then the type of the entire expression is integer. Otherwise, if the type of at least one operand in this expression is what? Is float, then the type of the entire expression is float. Okay? And we say this is naive approach. Naive approach. Why? Using this approach with a large number of what? Of times, the semantic functions become cumbersome. Can you imagine? For example, we also have double, another type, double. Is that right? And more. Using this approach, our program is very complicated. Is that right? Now, you all know that the type conversion rules vary from one language to another language. You know that. And in this example, we use type conversion rules in Java programming language. And you know, we define two auxiliary functions called max and widen. Okay. Now let's talk about max first. One thing I need to remind you that in common programming languages, including Java, conversions are limited to winding conversions. Okay? You understand? In many programming languages, implicit type conversions are limited to winding conversions. We have narrowing conversions and winding conversions. Using winding conversions, the information tends to be preserved. But using narrowing conversions, the information will be lost. Okay, so conversions or implicit type conversions in most programming languages are limited to winding conversions only. Okay, and this is winding hierarchy in Java programming language. Obviously, T1 and T2, they are input types, okay? And max function returns what? The least upper bound loop function of the two types. It means that if the type T1 is byte, the time T2 is character, then loop is what? Is integer, because it is the least of compound of the two types. We remember? And you see, based on winding hierarchy, a careful organization of mass can overcome the cumberousness of naive approach. A careful organization of mass, what does it mean? You can write a beautiful code of mass based on this winding hierarchy. Instead of writing what? This naive code. Do you understand? Now, what about winding? This pseudo function generates time conversions if needed to widen a very variable of time t into a very of time what? Time 2. Okay. Now look at this pseudo code. Obviously, if type t is also if t is also loop, okay, our function does nothing but returns the value. Otherwise, the value of type t will be converted to the value of what? Of type loop using this operator. It can be seen a converter. Okay, it's just pseudo function, pseudo operator, and then the new value of type loop will be returned. Is that clear? Now we need to rewrite our SDT using magic function. Obviously, we can determine the type of this expression. Is that right? If we confine ourselves to the type checking only, then the first semantic action is enough. Otherwise, if we need to compute the value of this expression, we use the next three semantic actions. Okay? Any questions? So